In this project, we developed an interactive visualization of the ARAP algorithm for surface modeling and introduced a weight painting method to enable heterogeneous deformations. Non-rigid deformation is essential in geometry processing, as real-world objects like clothing, soft materials, and the human body deform in complex ways. However, the standard ARAP algorithm applies a uniform deformation, failing to capture varying stiffness in different materials. Our contribution introduces a heterogeneous weighting method for more realistic deformations. The figure on the right illustrates this effect. The standard approach to mesh deformation enforces smoothness by constraining local vertices to move similarly, often using a wandering neighborhood as shown in the figure above. For heterogeneous deformation, one method modifies this by varying neighborhood sizes across the mesh to control local rigidity. Another approach, more similar to ours, applies a user-defined weight distribution within a specified range, scaling weights at different locations. We build on this idea in the next section. We will explain our contribution. Our first step was implementing the standard ARAP algorithm, which optimizes a cost function to maximize local rigidity per vertex fan. This is solved efficiently using an iterative approach. First, fixing deformed vertices to solve for rotations, then fixing rotations to solve for vertices. This so-called flip-flop optimization also ensures convergence. To handle non-uniformly shaped cells shown on the top right-hand side, the ARAP algorithm uses cotangent weights to avoid a discretization bias. However, as addressed before, this results in homogeneous deformation. To address this, we introduced a weight scaling approach using interactive weight painting. This method adjusts weights in specific areas by applying the formula below to achieve a more heterogeneous deformation. This difference between a homogeneous and heterogeneous deformation can be seen in the figure on the bottom right, where larger weights are applied on the stem of the left cactus and therefore resulting in less deformation in that area.
The application is implemented using OpenGL, and for the mathematical calculations Eigen is utilized. Additionally, the libraries ImGUI and ImGizmo are used to aid in the creation of GUI elements like buttons. The ARAP algorithm is computed on a different thread to decouple it from the user interface. Weight painting is implemented by rendering the triangle IDs into a texture. Afterwards, the texture is used by a compute shader to adjust the weights, which are then read back to the CPU to adjust the ARAP calculations.
We will now show the functionality of our tool. First, for basic ARAP. First, we select a mesh, in this case a cactus. To define which points move and which stay fixed, we place control points in edit mode. Once set, we switch to pose mode. In pose mode, every control point gets a gizmo allowing for rotation and translation. We also developed a heat map visualization for ARAP deformation energy, as shown here. Even after deforming the mesh, we can still add and adjust control points, which move in conjunction with the existing ones. For solving ARAP's minimization problem, we implemented several matrix decomposition algorithms, both sparse and dense, including Cholesky and QR. Thanks to our multi-threaded implementation, real-time feedback is possible, allowing for smooth and responsive deformations. Now in this demonstration, we'll showcase our weight painting functionality of our heterogeneous ARAP deformation using a spring mesh. Let us first look at the case of uniform weights. Now we enter edit mode and add control points which set the fixed and moved points for the ARAP algorithm. We select the top point and move it downward, squishing the spring into this new shape. Next, we visualize the deformation energy. Since the weights and the spring structure are uniform, the energy is evenly distributed. Now we can begin painting weights. We set a high weight of 5 and apply it to the middle of the spring, increasing its stiffness. Returning to post mode, we optimize ARAP with these new weights. As you can see, the middle expands due to its higher stiffness. The deformation is minimal in the painted area, and checking the weight map, we can see that the non-deformed regions match the high-weighted ones. Now we do the opposite, painting a low weight of 0.4 in the same area, reducing its stiffness. Back in pose mode, we optimize again, and instantly the previously rigid section now deforms the most and is squeezed between stiffer areas. Looking at the deformation energy, we see it concentrates where we painted lower weights. Finally, here's the weight map on the deformed mesh, showing exactly how the painted weights influence the deformation. In conclusion, we present an interactive ARAP framework that enables heterogeneous weighting through intuitive weight painting. This allows a seamless transition between rigid and flexible regions while preserving the mesh's original form. We run efficient iterative solvers on a separate thread, ensuring real-time performance and scalability across a range of mesh sizes.